Before we can fully understand how to calculate integrals using a change of variables, we need a few more notions here. So let's start with the notion of the Jacobian and what a Jacobian is. First, if you remember in the previous video, I snuck in a requirement. Let's see where that was. I think it was at the very beginning of the lecture. Yes, I snuck in this requirement here that all first order partial derivatives exist. You can see here I required that for a transformation x equals g of uv and y equals h of uv, I required that g sub u, g sub v, h sub u, and h sub v all exist. And in fact, for what we're going to be dealing with, I'm going to require slightly more. I'm going to also require that all of these four partial derivatives, I want to also require that they're continuous. And we'll give a definition for what kind of functions these are. If I can get to a new page, here we go. So let's start with a definition. And we're going to start with the definition of a so-called C1 function. So if a function f is so let's say if f is a continuous function, with continuous first order partial derivatives, we say f is a C1 function. And this 1 indicates at what order partial derivatives are still continuous, right? So this is first order partial derivatives are continuous. And so we can kind of make a list here. C0 functions are continuous. Not even necessarily differentiable. C0 functions are just continuous. So an example of a continuous function that's not differentiable is absolute value of x, right? This function's continuous. There's no discontinuities or jumps or anything like this, but the derivative doesn't exist at the origin, right? And C1 functions, these are all first order partials are continuous. Right? C2 would be all second order partials are continuous. And then C3 up to Cn, you get the idea. And then you get C infinity, which we say are smooth functions. This is all order partials are continuous. Right? So perfect example of a smooth function is a trig function or e to the x, right? You can take infinitely many derivatives and the derivatives are always still continuous because exponential functions and sine and cosine are continuous, right? So those are examples of smooth functions. We call them smooth functions, right? But for now, we really care about C1 functions. So now that we know what, remember we know what injective or a one-to-one transformation is, and now we know what a C1 function is, or a C1 transformation. So let's let t from S to R given by t of uv equals xy, let's let this be an injective C1 function. Or C1 transformation. I like the language we're using right now. I like transformation better. Okay, and let's try to construct the Jacobian here. So we have the UV plane, and let's imagine we have a very minuscule rectangle of the region S here, where this side length is given by delta U, and this side length is given by delta V. And let's say that the origin, or not the origin, sorry, the lower left corner of this rectangle is the point U0, V0. We have our transformation T. This transforms this tiny, tiny rectangle S, or of S, to some range in the XY plane. Maybe it's doing something like a kite, almost. Something like this, maybe. And we'll say, let's say that the point U naught, V naught maps to the point X naught, Y naught. Here, okay? And now, we can indicate where we're at. So also, let's say, sorry, let me be more specific about our transformation T here. Let's see our transformation T is given by X equals G of UV and Y equals H of UV. Okay, this is our transformation T here. Let's just, okay. We can indicate where we're at in this region R by a position vector, right? We can take a position vector here. We'll call this R of UV, these position vectors, to be G of UV I hat plus H of UV J hat, right? This is telling us exactly where we're at, because we know X is G of UV and Y is H of UV, so we can define a position vector or a family of position vectors that tell us, you know, whatever point you're at, you also have this vector, R of UV. And now we want to talk about the derivatives of this position vector. And to do that, let's look along a few particular lines. We can start along the line V equals V naught. So let's start by looking at the position vectors along this line. So let's consider the line V equals V naught. Well, the curve in the image, right? This line is going to map to some curve in the image, right? And what is that curve in the image going to be? Well, we can calculate that by looking at the position vector U V naught, because it's along the line V equals V naught, with tangent vector R sub U equals, well, the tangent vector is going to be composed of the partial derivatives, right? Because the tangent vectors, or the partial derivatives, live in the tangent plane, right? And so we have, this is G of U, U naught, V naught, I hat plus H sub U, U naught, V naught, right? And so basically we're just looking at something that's tangent to this line in the image. And this is what we'll get. Well, you can see that this is the parcel of X with respect to U, I hat, plus parcel of Y with respect to U, J hat. We can do the same thing for U equals U naught, right? Well, then we'll be looking at the image curve given by holding U constant at U naught and then varying V, right? What will its tangent vectors be? Well, the tangent vectors to this curve will be R sub V, which is going to be G of V, U naught, V naught, I hat, plus H of V, U naught, V naught, j hat. And so again, this will give us that r sub v is equal to partial x partial v I hat plus partial y partial v j hat. Okay, so here we're looking at u equals u naught, right? These give us curves with tangent vectors. So you could say, you could see something here that looks like this, and then something that looks like this for the tangent vectors of the image curves, right? And so here's what we want to do. We can see that this makes like a parallelogram. And this parallelogram could approximate the area of this rectangle R here. And so that's what we're trying to do. We're going to try to approximate the area of this, or of this region R by looking at the area of this parallelogram spanned with these sides here, given by the partial derivatives. And so we have that r sub u is dx du I hat plus dy du j hat, and then rb is similar but with the v coordinates. What we also know is the limit definition of these derivatives. So we have the limit for r sub u as delta u goes to 0 of r of u naught plus delta u v naught minus u naught v naught, right? This is the definition of the derivative at the point u naught v naught. Remember, we're always looking at the point u naught v naught here. And so this is over delta u. And similarly, r sub v is the limit as delta v approaches 0 of r of u naught v naught plus delta v minus r u naught v naught all over delta v. And if we're taking these limits as delta v and delta u are arbitrarily close to 0, well, then we get an approximation, right? You could kind of, it's silly, but you could think about multiplying delta u to the other side and then multiplying delta v to the other side. If you do that, we would get that r sub u times delta u is approximately r of u naught plus delta u v naught minus r of u naught v naught. And r sub v delta v is approximately r of u naught v naught plus delta v minus r of u naught v naught. And so what do we have here, right? Let's think about what these formulas are saying. We have that r of u naught v naught, right? So what is r of u naught v naught, first of all? R of u naught v naught is going to be the vector from the origin to the point x naught y naught, because x naught y naught is the image of u naught v naught, right? So we get this vector. And so what we're saying is that this difference, so what is r of u naught plus delta u v naught? Well, that's going to be a small change in the u direction and no change in the v direction, right? Which can get you something like this. We'll say this is r sub u delta u, right? Because these are approximately the same. And now here we get the same thing, but with a small change in v and no change in u. We get that this then is r sub v delta v, because it's a small change in v, like however the tangent curve is behaving, right? It has nothing to do with the directions u and v over here. It has to do with what the curves look like in the image. And so we have this r sub u delta u, r sub v delta v, and we can call this the area of this parallelogram. We can call this area delta A. And so now what we want to do is approximate delta A of the image of R by finding the area of the parallelogram with sides R sub u delta u and R sub v delta v. And so here I've been misleading with what I'm saying delta A is, right? Delta A is going to be the area of the region itself, of this tiny region R here, right? We can approximate the area of this tiny region R by finding the area of this parallelogram that we just constructed with sides R sub u delta u and R sub v delta v, right? This parallelogram will have some area to it, and we can approximate the area of this region R, and we'll say that this region is delta A, or the area is delta A of region R by calculating the area of the parallelogram. Well, we can use our notions from what we learned about vectors to calculate area. Remember, the area of a parallelogram is the same as the magnitude of the cross product, right? And so we can say, we can use R sub u to say that change in area, or this delta A, is approximately, well, not equal, sorry, approximately the magnitude of the cross product of R sub u cross R sub v, and then times delta u delta v. And so now to find the area, or this approximate area, we just need to calculate what R sub u cross R sub v is. Well, R sub u and R sub v are two-dimensional, so we'll need to throw in some zeros, right? Let's calculate what R sub u cross R sub v is. We can view these as three-dimensional vectors by adding zeros to the k component, and so R sub u was dx du, R sub v was dy du, or sorry, R sub u was dx du, dy du. R sub v was dx dv, dy dv. And you can notice when you take the cross product, well, everything in the I hat and j hat terms go to 0 because of these zeros here. And so that means we only have to look at the k hat component, and the k hat component is going to be the determinant of the 2 by 2 matrix dx du, dy du, dx dv, dy dv, k hat here. And so what this means is that delta A, the change in area, is I'll actually take this determinant up here, right? And that determinant is going to be dx du, dy dv minus dx dv, dy du times delta u delta v. And now this value here, this determinant, right? Or this value here in its expanded form, is a very, very, very important concept in a lot of mathematics, especially analysis and calculus. So definition, the Jacobian of the C1 transformation T of uv equals xy is, and so we'll denote by the Jacobian in variables uv. And so we say j of uv is equal to dx du dy, du, dx, dv, dy, dv. It is a matrix, right? It's a 2x2 matrix composed of all first order partial derivatives, right? You can see here is first order partial derivatives and first order partial derivatives with respect to u. Here's first order partial derivatives with respect to v. Okay. And so this whole construction was to first give us where the Jacobian is showing up. But second, it's to define integrals in a change of, it's to define multiple integrals in a change of variables. And so we'll come back to this in 1 second. I want to first talk about the Jacobian a little more, just to like do an example, really. So let's find the Jacobian of T of uv equals u squared minus v squared uv. Okay, so we used this transformation in the last video. And so the Jacobian of this transformation is, well, let's remember, it's the partial derivative of x with respect to u, partial derivative of y with respect to u, right? That should be a partial. And then what am I doing? Partial derivative of x with respect to v, partial derivative of y with respect to v, right? Well, this is the determinant. Let's plug in the partial derivatives. dx du, partial derivative of x with respect to u. So we get 2u. Partial derivative of y with respect to u is v. Partial derivative of x with respect to v is negative 2v. Partial derivative of y with respect to v is u. And so taking the Jacobian, looks like we're going to get 2u squared minus a negative 2v squared, so plus 2v squared. And so here's an example of calculating the Jacobian, right? It's just calculating partial derivatives and then setting up the appropriate matrix. Okay, so now that we've seen what the Jacobian is, we've gone through this entire construction to approximate the area of this region R, because the whole point is that we want to set up the double integral involved in this transformation, right? And so now let's put everything together here. We have, for double integrals, what do we have? Well, we have that double integral over the region R of f of xy dA. This was as a limit, the limit as m and n approach infinity of the double sum I equals 1 to m, j equals 1 to n of f of xij star. Remember, these were test points, yij star delta a. But now we know what delta a is. Excuse me. We know what delta a is. We went through this entire construction to figure out that it's the Jacobian times delta u delta v. And so because of that, we get that this formula is the same as the limit as m and n go to infinity of sum I equals 1 to m, j equals 1 to n, f of x I j star y I j star times the Jacobian times delta u delta v. And so we get this nice theorem that the double integral over the region R of f of xy dA is equal to the double integral over the region S, right, over the domain of f of, and now we plug everything in, right? Well, in the over region R, we're in the variables x, y, but over the region S, we're in the variables uv. So this is f of g of uv, h of uv, times the Jacobian of uv du dv. And so now we can talk about calculating integrals via a change of variables using Jacobians. So what this is saying is that, okay, well, you want to find the double integral over some region R, right? You want to, let's look back to our picture here. Say you want to find the double integral over this region R here. Well, over this region R, maybe it's really complicated. We can find the double integral over the region S, which is a much nicer region. Like here, it was just a rectangle, right? And we can find the integral over the region S by subbing in everything in terms of u and v, and then including the Jacobian in our formula. That's exactly what this theorem is saying. It's saying the integral over the region R is the same as the integral over the region S, where you've plugged in u and v, and you've included the Jacobian. That's how we can set up a change of variables for double integrals. And let's look at the Jacobian. Let's look at the 3×3 Jacobian now. Right? There's an n by n Jacobian, right? So if you have a function of n variables, then the Jacobian is an n by n matrix. So let's consider t goes from S to R given by t of u v w equals x, y, z, where x is equal to g of u v w, y is equal to g of u v w, and z is sorry. Y is equal to h of u v w, and z is equal to k of u v w, right? And so we have this 3×3 transformation now that would be taking some 3D region and mapping it to some other 3D region, maybe like this, right? We would have S, T, R, something like this, okay? And now we want the Jacobian for the transformation T. Well, the Jacobian, J of U, V, W, is the 3×3 matrix of partial derivatives, right? It's partial derivatives with respect to u first. So dx, du, dy, du, dz, du. That should be a u there. And then the second row is partial derivatives with respect to v. So dx, dv, dy, dv, dz, dv, and then the last one is with respect to w. So dx, dw, dy, dw, dz, dw. And so here's the Jacobian for a transformation of 3 variables, right? Like you're transforming from a 3-variable region to a 3-variable region. And then we have an analogous theorem that says the triple integral over the region R of f of x, y, z dv. So I should clarify in my pictures here that R is in x, y, z, and then S was in u, v, w, right? We have that this is the same as the triple integral over the region S of f of, and then you plug everything in. So you plug everything in u, v, and w. So g of u, v, w, h of u, v, w, k of u, v, w, and I'm out of room here, but this is times the Jacobian in these 3 variables, which is to be calculated right here. And then du, dv, dw. And so we have an analogous 3-dimensional theorem for using the Jacobian when calculating integrals under transformations. And so these can be very helpful because you can pass from a quite complicated region to a relatively simple region just by substituting u, v, and w in for x and y, right? Or substituting the appropriate functions in, and then taking the Jacobian. And then you have the triple integral set up over the region S, and you can finish by calculating the integral. And so this wraps up what I wanted to discuss about multiple integration. Right now we've been through multiple differentiation, and we've been through multiple integration. There are applications of all of this stuff. And one of the first applications that we can look in depth at is vector calculus. And so we're going to, for the remainder of the course, we're going to step into the realm of vector calculus. And we can see what vector fields are, what's the curl, what's the divergence. We get some really nice theorems attributed to mathematicians like Stokes and Green. We get some really nice theorems that are quite powerful for computation. And so from here, we'll now dive into the interesting topics of vector calculus.